Good morning. Okie dokie, it's 10 o'clock. So, before we get going with going through the homework, first, I would say much better job of getting your stuff done. Good job. I think just about everybody got their homework in on time. And there's one person who talked to me ahead of time last night and said, hey, I got a lot of homework. Can I get an extension? I said, sure. So part of growing up is looking at your workload ahead of time and saying, hey, I got all these different projects. I can't get them all done in time. So you got to go back to your boss and say, we got to move some deadlines around. You don't walk into a meeting 5 minutes before the meeting and say, yeah, I couldn't get it done. You got to talk to your boss ahead of time and move the date of the meeting so that you are prepared. So just keep that in mind. Then the second thing is starting next week, Tuesday, half of you will be here with me face to face, and the other half will be at home. So when you're at home, the class is going to run just like normal. I will be giving you notes through Notability. So I will have my iPad and I will be writing my notes on the iPad so that people at home can see it because I'll be sharing my screen. For those of you who are coming face to face, there might be a little few hiccups along the road with audio. So we'll figure it out, okay? Because what we may have trouble with is if there are two open mics in the room at the same time. So right now, I've got my computer on, and my computer has its microphone on. You should see, if you look in the participants, you see two of me. There's Jason Strauss, host, and then there's Jason Strauss, not host. The host is my computer, and I've got the microphone on my computer so that I can record the lesson. And so those of you at home are hearing me through my computer. I turn down the volume on my iPad so that I don't get feedback, because basically I have two microphones, my computer and my iPad. If both of them are operating at the same time, sound will go from my computer through my iPad, back to my computer through the iPad, and then you end up with a feedback loop, which is hence called feedback. So this is what it sounds like when I have both microphones going, So there was bad feedback, right? Yep, okay. So when I turn the volume down, I guess I'm a little surprised. You guys don't get feedback when the volume's turned down on my iPad?
Yeah, like right now, there's no feedback.
Okay, well, I guess we'll find out, because for those of you who are in class, you may, I don't know how you're taking notes right now. You may decide to continue to take notes on paper and pencil. You may decide to take notes in Notability. I don't know. That's really up to you. But for those of you who come to class, the notes are going to be projected up onto a big screen TV. So you'll be taking notes off the big screen TV. So you don't need your iPad per se, but you may find it that you like to have the iPad out and be looking at your iPad during class. If that's the case, you're going to have to make sure that your volume is turned all the way down. Otherwise, if we have 12 open mics in the room, we'll probably get pretty bad feedback. So you'll have to turn the volume down all the way. Or if you don't want to turn the volume down all the way, you'll have to wear headphones, okay? When students at home ask a question, I will repeat it in the classroom. Because if you ask a question at home, it's going to come through my computer, and it probably won't be loud enough for people in the classroom to hear. So I will repeat your question so that the students in the classroom can hear. I'm going to show you how to turn off your mic, and I'm not talking about muting. Like when you look at the screen of participants, you see no mic, no mic, no mic, no mic, no mic. And then for Jackson Deering, for some reason, it says he's connecting to audio and it's still trying to connect. So I'm not sure what's going on with Jackson, but because you can see a slash through the mic, it means you're muted. Jackson is not connected to the audio. Actually, let me share my screen here. That's probably better instead of just. All right, so you see all the students? If the microphone is red with a slash through it, it means you're muted. If your microphone doesn't appear, like with Jackson, boy, this has actually turned out great. Thanks, Jackson. You're actually helping me out here.
I'm not sure if we're seeing the same thing. We're just seeing your email right now.
What? Not my email. Oh, it doesn't. I guess it doesn't show itself.
Maybe if you were to do it on your iPad, like, is it possible for you to like record audio or record video on your iPad and then just show your screen?
I cannot record video on my iPad because my iPad doesn't have enough storage. It'll max out pretty quick.
Isn't there a video or like a setting where you can like use your camera and show stuff?
Yeah. I would say it's not all that critical, because I can just tell you. So all I was going to say is, if you see a microphone, it means your microphone is active. It's just muted. If you don't see a microphone, it means you're not connected to audio at all. So we may have you disconnect audio, and I'm going to show it to you right now just because it might be helpful, not just in this class, but other classes. So I'm going to switch over to my iPad here, and I'll just show you how to disconnect the audio. It's pretty simple from the iPad. Hopefully this works. It doesn't. So I'll just tell you, from Zoom, if you go under more, where you can raise your hand or you can click on the chat. If you go down to the disconnect audio, it'll make your microphone disappear. and then the microphone is completely turned off. It's not just muted, the microphone is turned off. So if I, there I go. So I just turned off my microphone completely. That's for people who are in class. So Lucia said, if you turn off your microphone, you won't be able to hear. If you're in class, you can hear me from my own voice. So we'll see how it goes on Monday. We might have people turning off their microphones, we may not. It depends if we have feedback, we'll figure it out. But if you go under more, you can disconnect from the audio, and that should take care of feedback issues. Okay.
Wait, Jess, can I ask a question?
Sure.
Why, if we're like in person, like in your classroom,
Yep.
like on the days like our group is in person, why would we be logged into Zoom?
You wouldn't have to. You wouldn't have to, but the option is there for, let's say, perhaps you want to take, perhaps you want to follow along on the iPad versus, I've got a big screen TV to project the notes up onto, so you should be able to see the notes on the board well enough if you're face to face, but we're going to find out. Maybe the writing will be too tiny. I don't think it will be. So you always have the option of following along on your iPad as well if you're face to face.
Do you think it would just like make it easier for you if we all just agreed to like not log on to Zoom in the classroom, just so like there's no technological problems for people like at home? Because I feel like we could do that.
Well, let's just wait and see, because like I said, it's going to be hard to tell if the projection's going to be too small or not, or maybe I can zoom in on my iPad, but all I'm trying to say is there's going to be a few hiccups the first few days, but we'll work them out.
Okay, perfect. Thank you.
And be patient with your other teachers as well. Okay. Any other questions about next week before we, oh, here we go. Here's a question. If we have an in-person day and we just join Zoom instead, will we be marked absent? That's a good question. So, my guess is, yeah, I actually now, yes, you will be marked absent. So if you sign up for face-to-face and you don't show up to class, your parents have to call you in as to being sick or whatever, or what's going on. Okay. So your parents will have to call you in just like before. Now you can still join in via Zoom, but we need to know where people are. So if you don't come to school, you need to, and similarly, if you don't log in at home, we mark you absent as well, if you're all completely virtual. Does that answer your question, Lucia? All right, let's start going through the homework problems. All right. So these you probably found a little bit easier than the other ones. So I don't plan on going through all the problems, but I definitely can if there are ones that you want me to go through. So I'm going to do 59B. Because these are elementary steps, we can figure out the rate orders just by looking at the molar coefficients. So because ozone has got a 1 in front of it, and because nitrous oxide has a 1 in front of it, we can just replace the rate orders like that. Okay. D. Now remember, we can only do this for elementary steps. So that's a 1 and that's a 1. So I just go boop, boop, 1 and 1. All right. So there are questions on number 59. Okay, so a proposed mechanism so that's step 1. So first this has to break apart. And that step is slow. Then what happens is the C4, oh, that's a 9. C4H9 plus becomes C4H9OH plus, and that step is fast. Then this thing reacts in step 3 with water to produce C4H9OH plus H3O plus, and that step is fast. So what's the overall reaction? So we add things up and see if they cancel, kind of almost like Hess's law. So that cancels with that. That cancels with that. And so what's left is C4H9Br plus 2 waters goes to C4H9OH plus a bromide ion plus H3O plus. Okay. So that's the overall reaction. Now, in the previous problem sets, we determined the rate law by looking at data. And then we had to do all this wonderful math to solve for N and M. But if they give us the reaction mechanism, your overall reaction can only proceed as fast as the slowest step. Okay, like that analogy I said, a group of hikers can only hike as fast as the slowest hiker. So my slowest step is the first step. So that means, for elementary steps, I can just raise them to their power. There's a 1 there. Okay. So this is where sometimes it might be a little bit strange in that the first set of problem sets, we were doing this. Now, this is the actual rate law for the overall reaction. Guess what? Oh, wait a minute. Did I make sure I write that right? Yep. Sometimes there will be things that don't appear in the overall rate law. Okay. For example, just pretend for a second that this was the slowest step. If that was the slowest step, then my rate law would be this. And as you can tell, C4H9 plus does not appear anywhere in my overall reaction. So sometimes the rate of a reaction depends on an intermediate. Now remember, an intermediate is produced in one reaction and consumed in another. So this is an intermediate. The C4H9 is an intermediate because it is produced in reaction number 1, but then consumed in reaction number 2. So it may be that your rate law for your overall reaction might have something that doesn't appear in the overall reaction. Okay, that is possible. All right. So let's go back to the actual problem where the first step was the slowest. So we know, again, that the rate law for the overall reaction is the slowest step. So I use the information from the slowest step to create the rate law for the overall reaction. So what is the rate order for C4H9Br? What's my N? What is the value of N for C4H9Br? You bet. Nice job. So I know that N is 1. Now this is where I was trying to go. What's the rate order for water? Well, do you see water in my rate law? No, you don't. And the reason why you don't see it is exactly right, Lucia, because M is 0. So if the rate law for something is 0, something to the 0 power is 1. So in a sense, the water disappears from, so there's your overall reaction. Okay. Let's see if there are any catalysts. Is something used up in one reaction and produced in another? No, I don't see it. Any questions on 61? All right, 64. So they want you to draw a rough sketch, and it should be roughly to scale. It doesn't have to be perfect. So the energy change is plus 10. So that means it has to be endothermic. So this difference is 10 kilojoules. And my activation energy is the height of the hill. B, we're getting 10 out. So if I'm getting 10 out, I should probably stay consistent with what I'm doing in A color-wise. So negative 10, it's exothermic. And the height of the hill is 50. And C, I'm getting out 50 kilojoules, so it's exo. And the height of my hill is 50. So the height of my hill, and so those two heights should be roughly the same. All right. So we're almost done with all the information. Okay. Now this is a tough chapter, so you're going to need a lot more practice. So you're going to get some homework tonight, I hope. Well, you are. And I'm also going to give you the practice test. I can show this to you. So the chapter 12 review. So you've got the worksheet and then the answers with you. Okay. Even if we don't get through all the material today, start working on it. There are most of the stuff you know how to do. And it's due next week, Wednesday. Don't wait till Tuesday night. You won't get it done. Okay. Start doing like 5 or 6 problems a day. Okay. And this is going to be hard. So please don't give up and just say, oh, I don't get it. I give up. These problems are tricky. Okay. But that's why we're taking AP Chem now, so that when you get to college, it'll be a lot easier. Just like when you look at chemistry class, it looks like child's play because they're balancing reactions. And you're like, oh, that's so easy. All I got to do is balance. But when you first learned it, it was hard. Okay. So similarly, when you're in college and then you're studying this stuff for the second time, it'll be a lot easier. Okay. So you got to promise me you don't give up. And yes, the test is curved, just like all the others, they're curved. So when you take the test, the key is you got to go through and answer all the questions you know first, then go back and kind of guess at the questions you sort of know, or maybe can eliminate some wrong answers. And there's going to be some that are just left blank. Okay. And you just have to be okay with that. It's not about getting every question right. It's about maximizing your points. Okay. So that you, and that's just the way the AP exam works. On the AP Chem exam, a 50% is a 3. I think an AP Psych, an 80% is a 3. So not every AP test uses the same curve. AP Chem is one of the tougher ones. Not 60 multiple choice questions in 90 minutes. You're not going to answer them all. It's impossible. So right from the get-go, they've designed the test so that it's impossible to get through them all. So you're going to be guessing on a lot of those multiple choice questions. Okay. So the key is don't give up, Aiden. All right. So when you take the test, don't give up. You know more than you think. And you get partial credit on the free response and the multiple choice. You can eliminate the wrong answers and guess, and you get pretty good odds. Okay. It's a new game. So this homework, like I said, start it tonight. Don't wait. Start picking away at it. And we'll see. My plan is for us to do a lab on Wednesday and Thursday. So it might be that on one of those days you have a work day on this assignment and the other day you do the lab. And if you're completely virtual, I'll give you lab data. Okay. And my plan right now is to start doing the labs from first semester. So it won't match completely with what we're studying. But it's good that we do those labs anyhow. Is the test just on the stuff we've learned so far? Yes. But it's kind of like math class. Things build on one another. So you can't just forget or ignore the information you learned first semester. Okay. All right. I know that was a lot of talking, but it was important talking. All right, new material. So as temperature increases, the number of collisions increase. Remember, you can't react if you don't collide. You got to collide. So if we want to increase the rate of the reaction, increase the temperature, because by increasing the temperature, you will increase the number of collisions. The more collisions, the more likelihood eventually you'll find a reaction. So if we want to go back to dating, you know, when I was trying to find a date for a prom, I just went down the line. First person said no, went to the second one, then the third, fourth, fifth, sixth. Eventually, you find someone who says yes. Eventually, you get to a reaction. So the more collisions, the more likely you're going to react. Now, just because you collide doesn't mean you're going to react, okay? There is a energy threshold, and that is the activation energy. So a collision must have enough energy to overcome the activation energy hill. So the activation energy hill basically is you're breaking the bonds of the things that are going to react. So you got to break the bonds first to then reform new bonds. So for example, if hydrogen and nitrogen are going to react, I must first break those bonds before I can reorganize them into a new compound. Okay, I know that reaction isn't balanced, but I'm just trying to explain to you what is the activation energy hill. It's the energy required to break the bonds. And for every reaction, it's different, how much energy it takes to break those bonds. So the rate constant is dependent upon the following things. First of all, the collision frequency. So how often do the things collide? P is what we call the effective collisions, meaning collisions with the correct orientation. Correct orientation in space. And kind of the fancy word for correct orientation in space is steric. Steric means the orientation in space matters. All right. And the example I gave you, if you're going to ask somebody out on a date, don't approach them from behind and tap them on come up from behind and whisper in their ear, hey, you want to go on a date? That's going to freak them out. Okay. The wrong orientation. You're approaching from behind. Approach from the front. That's the correct steric orientation. We see that more like in biochemistry. I suppose I need to give you an example. For example, acids. And if you want to write this example down, it's up to you. But I just wanted to give you an example of a steric reaction. So water likes to steal the hydrogen. Well, it can't steal the hydrogen if it approaches the molecule from the other side. So even if these two things collide with the right energy, they won't react because it didn't collide from the correct side, or we'd say the steric. All right, so you got to collide, you got to have enough energy, you got to collide from the correct direction, and then you should be able to react. That's the exponential function. EA is activation energy. So how much energy is it going to require to break those bonds? R is the universal gas constant, and T is temperature. And the universal gas constant that you're going to have to use is 8.31 liters kPa per mole Kelvin. Temperature must be in Kelvin. And K is the rate constant. So just to kind of recap here, the rate constant depends on how often you collide, how many collisions are effective, meaning how many collisions approach from the right side of the molecule, how strong are the bonds you have to break, and what temperature are we operating at, okay? Activation energy is in joules. Temperature is in Kelvin. So what about liters in kPa? How do those things cancel? A liter kPa is a joule. And I mentioned this back in chapter 5 when we were studying gas laws, but I'm just reminding you that a liter times a kPa is a joule. So that means a liter times a kPa is a joule. So that's where we get our joules from in the equation. And again, the further you go on in science, when you're studying, you should be thinking, how do these units cancel? Because if the units don't cancel correctly, something's wrong. So anytime you're doing a problem, you should always be thinking, are my units canceling correctly? Because that doesn't lie. You never get the right answer and have the wrong units. So what questions do you have so far on the equation for K? Another way that equation can be written is they kind of simplify it. Z times P is called the frequency factor. Basically, it's a percentage of the effective collisions. So Z just tells me how many times the molecules collide. P tells me how many of those are going to be colliding from the correct orientation. So it's the A variable down there, frequency factor, is basically a percentage of how many collisions will be effective. Okay, so this equation then can be rewritten as this. So there are only two things that affect or can change K: temperature and a catalyst. So why does temperature affects K? Because it increases the kinetic energy of the molecule. So temperature affects A because it increases the kinetic energy of the molecule. And therefore, it has more energy. I should say, let me change it. There are more molecules. There are more molecules that have enough energy to overcome the hill. So T affects K because it increases the kinetic energy of the molecules, and therefore there are more molecules that will have enough energy to overcome the activation energy hill. The catalyst affects K because it decreases the activation energy. Therefore, activation energy hill. Therefore, more molecules can make it over the hill. So I did draw this picture before. When you add a catalyst, it lowers the activation energy hill. So there are only two things that affect K, the rate constant: temperature and the catalyst. Both of them will increase K. They will make K bigger. because if you're going to speed up a rate, I'm just using a generic letter A here. If you're going to speed up a rate, you're going to have K become bigger. So K becomes bigger by adding a catalyst, or K becomes bigger by increasing the temperature. And those are the only two things that affect it. All right. So I can take my equation over here that I had, and I can change the form of it. I can take the ln of both sides. And I do that to get my exponent down. If I do that, I get ln of k is equal to negative EA over R, 1 over T plus the ln of A. And this is not that A. That A is this A up here, the frequency factor. I'm just going to go 5 minutes more, then I'm going to give you your homework. I just want to finish the chapter. But then in parentheses, why am I putting it in parentheses? So that it looks a little bit more like the equation of a line. So x is 1 over T. The y-intercept is the ln of A. My slope is negative EA over R. And my y is the ln of K. This is called the one-point form of the Uranus equation. Uranus was the scientist who worked on this. So this is the one-point form. Why is it called one point? Because it's only got one temperature and one K value. Now, what happens to K if I increase the temperature? That's when we use the two-point form. The two-point form is going to have two temperatures and two K values. Notice that the EOA over R is now positive. It's the first temperature minus the second temperature. And due to time, I'm not going to show you how this equation was derived, but basically and I don't know if the book did it, if you want to do this for fun. I'm not going to work through the steps, but to get the two-point form, you take the one-point form, and you divide it by the second one. So I could walk you through the algebra, but I'm not going to. But if you do this, you will get this equation. Okay? Maybe I'll do it next class period. I don't know. We will use this equation more often because it's easier to get the EA, the activation energy. And we will do a lab with this. It's a really nice lab. It really proves the importance of these equations, but the lab is a beast. It is something that takes us 2 to 3 days to walk through.
What's the name of the person who made the
Uranus, ARRENHIUS. He did a lot of other things too, but So for homework, I'd like you to do number 69, 75, and 69, 75, 79. And actually, maybe I'll do them in order. On page 592, do numbers 4, 9, 11, 13, 17. These are tricky. 17, 19, 20, and then 69, 75, 79. All of these, almost all of those are theory questions. So there's no math, okay? 69 and 75 are math questions. And then 79 is a theory one. So why don't you try those problems, and I will schedule an office hours for Monday in the afternoon to help you with these things if you want. Maybe, what would be a good time on Monday to schedule an office hours for? It's like 1 o'clock good? So if you want to get extra help, I'll schedule office hours Monday at 1 p.m. Also Tuesday morning at 9 a.m. So for those of you who want to log off, feel free. Otherwise, I'm going to kind of help set up number 69 and number 79 for those of you who want some help right now. Okay? So for number 69, it says the activation energy for the decomposition of HI, hydroiodic acid, to hydrogen and iodine. I'm going to balance my reaction, put a 2 there. It says the activation energy is 186 kilojoules per mole. The rate constant at 555 degrees Kelvin is 3.52 times 10 to the -7th liters per molar. What is the rate constant at 645? So if they give you 2 rate constants, that means you have to use the 2-point form. All right? The 2-point form is the ln of K1 over K2 EA over R T1 over T2. And the nice thing about the 2-point form is this thing drops out. We don't need to know the A variable. That's why we use the 2-point form more often. Where people usually go wrong is making sure they understand which one is K1 and which one is K2. So I'm going to call that one K1. I'm going to call this one K2. This one's at 645, which means that this would be T1 and this would be T2. After years of college and years of teaching, people plug things in the wrong spot. That's why I have you write down the variables, so you plug things in the correct area. So now you should just be able to plug and chug and finish the problem off. So that's number 69. Number 71 or 75 is the one that you would struggle with is 75C. It says you've got an uncatalyzed reaction. And the activation energy for the uncatalyzed is 14 kilojoules per mole. When you add a catalyst, it's going to lower the activation energy hill. What is the ratio of the rate constant for the catalyzed reaction to the uncatalyzed? So what is the ratio of the catalyzed to the uncatalyzed? So that's a ratio. Of the K values, the K values of the catalyzed over the uncatalyzed. The ratio of the K values, cat to uncat. So this is a situation where you would use the, where's that 2-point form? No, we'd use the 1-point form. So I'm going to write the 1-point form. So we want the ratio of this to this. The temperature is not changing. And then the problem says to assume that the frequency factor is the same. Oh, they tell us the temperature, even better. So the temperature is 25 Celsius or 298 Kelvin. So before so now we got to have some fun algebra here. Probably the thing you want to do first is take care of this side. So I would plug in the 298 and the R value. Well, I suppose we can just distribute first. and then we're going to combine those. All right. So I'm running out of time here and I want to be respectful. So that's a good start. You're just going to have to do the algebra, and then eventually you're going to have to take the exponential of both sides to get rid of that, to get rid of your natural log. Okay. A and B are easier, but C's a little bit. Okay. So I will post the homework problems online, and I will set up office hours for Monday at 1 o'clock and Tuesday morning at 9 a.m. Okay. You guys have a wonderful weekend and start working on your problems tonight.
Thank you.
Thank you, guys.
Thank you.